The following content is provided by MIT OpenCourseWare under a Creative Commons license. Additional information about our license and MIT OpenCourseWare in general is available at ocw.mit.edu.
Sometimes called the van der Waals interactions. And we saw that we could make a molecule between two inert gas atoms like argon-2 or xenon-2 by virtue of these dispersion interactions, where the instantaneous charge fluctuation in one atom or molecule then produces a dipole. That dipole then induces a dipole in the neighboring molecule, and the result is a stabilization, an attraction. And we saw last time how we had a generic form for the interaction potential for the dispersion interactions, this Lennard-Jones interaction potential. We talked about that in detail. And one of the parameters in that Lennard-Jones potential was this quantity epsilon, which actually was the well depth. And I just wanted to talk a few moments here about what determines what the well depth is, what the strength of that interaction is. And the bottom line is what determines that is the polarizability. The polarizability of the atoms or the molecules that are interacting. And we give the symbol alpha to the polarizability. And what that is a measure of the ease with which a charge distribution can be distorted. That's the polarizability of the molecule. That is a term you will hear in future courses quite a lot. And in general, the polarizability goes up with the number of electrons present. All right, so as you go from, and you can see on the side slides here, as you go from helium to argon to xenon, and let me either fix my pointer. Okay, as we go from helium, argon to xenon, this polarizability goes up because the number of electrons are going up. If the number of electrons are going up, that means we have electrons in outer shells. They're farther away from the nucleus. Hey, they're more easily distorted. All right? So here, as this polarizability goes up, helium, argon, xenon, that well depth for the Lennard-Jones potential is going up. Right? 0.085, 0.996, 1.8. And here on this diagram, I actually show you what the shape of the Lennard-Jones potential is. Sometimes when I draw it on the board, it's not so accurate, but you can see this Lennard-Jones potential actually has this repulsive wall that goes up really very steeply. Okay? And likewise, on the next slide, you see some interactions for at least one molecule here, helium, nitrogen, argon. You can also have these dispersion interactions, and you do have them between molecules, right? So the polarizability here is going up, helium, nitrogen, argon. The well depth is going up. And again, these are the Lennard-Jones potentials for those inert gases and for the interactions between two nitrogen atoms, dispersion interactions. So all atoms and molecules have these dispersion interactions. It's just that sometimes oftentimes the dispersion interactions can be so weak compared to some other interactions, which we're going to look at today, that we don't even think about them, but they're actually there. Okay, but what I want to do now is to talk about what happens as we lower the temperature even further. In other words, last time we were talking about the deviation from the inert gas law as we lowered the temperature. And what we said is that it is these dispersion interactions that are the microscopic origin for the deviation from the inert gas law, which is a macroscopic law, all right, as you lower the temperature. But we also know that if you lower the temperature enough, that the gas condenses, the gas liquefies. And it's these dispersion interactions that are also responsible for the condensation of these gases. But now let's talk about a little bit more deeply what exactly is going on as we lower the temperature, as we lower the temperature close to the liquefaction point. All right, so let me draw a Leonard-Jones potential again. And now I'm going to do it for two nitrogen molecules. So here's nitrogen, two separated nitrogens as a function of R, the distance between the two nuclei. This is our zero of interaction right here. Okay? And I said from that slide that this bond dissociation energy measured from the bottom of the well here is 0.79 kilojoules per mole, the bottom of the well where the molecules actually can never be. Okay? Okay, but that's the well depth. Now, let's think about this. At 300 degrees Kelvin, right, what is the average energy of the molecules? Well, the average energy is 3/2 RT, as we saw. And if I substitute in this temperature, well, I'm going to get something on the order of 3.7 kilojoules per mole. Okay, if this has two significant figures. 3.7 kilojoules per mole. Well, let me do the following. Let me draw 3.7 kilojoules per mole here on this Leonard-Jones potential. Well, when I do that, and I'm going to start here at the bottom of the well, and I draw 3.7 kilojoules per mole, well, that's somewhere way up here, right, compared to the interaction energy. So at 300 degrees Kelvin, the bottom line is that those two nitrogen molecules have enough kinetic energy to totally ignore this interaction potential energy, this interaction energy, right? They're way up here. If they have 3.7 kilojoules per mole of energy, hey, they're not going to stick together. They're not going to condense. They're actually really going to ignore this small interaction energy. They're going to just fly apart. And they do. You have a gas, right? However, let's lower the temperature now. Say we lower the temperature to 100 degrees Kelvin. Well, when we do that and we calculate the average energy at 100 degrees Kelvin, well, that's on the order of 1.2 or so kilojoules per mole average energy. Okay, 1.2 kilojoules per mole, well, we're somewhere here, right? 1.2 kilojoules per mole. And now, you know, the relative energies between these nitrogen molecules is much lower, and it's beginning to be comparable to this well depth. And you know what? Those nitrogen molecules now are deviating from the inert gas law. They're kind of hanging around each other. They don't hit the walls as often, the walls of the vessel that they're in. They don't hit them as often because they're having an attractive interaction with their neighboring nitrogen molecule. And so we're deviating here from the inert gas law. The pressure isn't as large if you're doing it under constant volume conditions. And then, say we lower the temperature to 77 degrees Kelvin. 77 degrees Kelvin is actually the boiling point of nitrogen. make liquid nitrogen, 77 degrees Kelvin. Well, at 77 degrees Kelvin, the kinetic energy is 0.96 kilojoules per mole. And now, in this case, well, we are fairly comparable to the well depth, right? Here at 0.96 kilojoules per mole. What happens is the gas condenses, right? The interaction energy between those two nitrogen molecules is on the order of their kinetic energy. And then these molecules stick together. The gas condenses and you have a liquid. All right, so that's the origin here of this temperature dependence and the relevance to the microscopic interactions between the molecules. All right, we can understand that. Okay. And then vice versa, if you start to raise the temperature, well, the molecules start to fly apart. They ignore this interaction. Their energy is greater than that attractive interaction. And so what you can see in the macroscopic boiling points then, what you can see is the vestiges of this microscopic interaction energy. So for example, and now I'm going to, I think I'm going to put the center screen down. I mean, if you look at here, helium, if you look at helium, neon, helium, neon, argon, krypton, xenon here. And what we said is that this polarizability here increases as we increase the number of electrons. You can see that that well depth increases. Therefore, the boiling point increases as we go down then the inert gas column. All right, so you can see how that boiling point, that macroscopic boiling point, is a reflection of what's happening on the microscopic scale between two individual molecules. You can also see that here in this plot, or in this chart. Here we've got molecules, hydrogen, nitrogen, oxygen. The polarizability alpha is also increasing as we go down. Correspondingly, the well depth is increasing. Correspondingly here, that boiling point is also getting larger and larger. So that macroscopic quantity then reflects the change in the individual interaction energies between the molecules, the microscopic quantity. Okay, but it also turns out that the shape of the molecules are important. So for example, let's take this molecule, C5H12. There's several ways I can draw a skeletal structure for C5H12. One way is to make it pentane, making it a linear molecule. All right? And another way is to make this 2,2-dimethylpropane. Carbon in the center, some methyl groups around that center carbon. Turns out that the boiling point of pentane is 309 degrees Kelvin. The boiling point of 2,2-dimethylpropane is 283 degrees Kelvin. Hey, these are two molecules here which have the same number of atoms, i.e. the same number of electrons, should have the same polarizability. However, one has a higher boiling point than the other. And the reason for this is because of the different shapes of these molecules. In the case of propane, if we have an instantaneous fluctuation in our charge distribution, well, that instantaneous fluctuation is going to be essentially along a line. That instantaneous fluctuation is essentially kind of rod-like because of the skeletal nature of the pentane. So one end is a little positive, one end's a little negative, the other way around. That's going to induce a dipole in a neighboring pentane molecule, and then they're going to align, positive, negative here, positive, negative there. Okay? But then, in the case of dimethylpropane, you're also going to have this charge fluctuation. But in the case of propane here, this is a more spherical looking molecule, and so the charge fluctuation isn't going to be so rod-like. But nevertheless, this charge fluctuation induced dipole here is going to induce another dipole in a neighboring molecule, and you're going to have an attractive interaction. But in the case of the 2,2-dimethylpropane, hey, this is a much more spherical distribution than this. In this case, these two dipoles aren't as close together as they are in the case of pentane, meaning that the interaction energy here between the dimethylpropane is going to be less than it is in the case of the pentane. And again, that is reflected in the macroscopic boiling points. The boiling point of pentane is larger than that of dimethylpropane, because that microscopic interaction energy is larger for propane because the dipoles, the induced dipoles, can get closer together. Okay? So the shape is also important in determining these boiling points, these energies of interactions. Okay. So that's going to take care of our discussion of molecules, or discussion of the induced dipole interaction energy, where we're talking about molecules that don't have permanent dipole moments. But now we're going to turn to molecules with permanent dipole moments, such as HCl. And of course, in these molecules, the dispersion interaction is also taking place. It's just that that's going to be weak compared to now the interaction between two permanent dipoles. Okay? So here we have HCl. Here's one HCl molecule, permanent dipole. It's going to then, in a collection of HCl molecules, attract another HCl molecule, and that HCl molecule is going to align in the opposite direction. The alignment of those two dipoles, hey, that's going to lower the energy. That's the attractive interaction. And then you might say, but, hey, you get this attractive interaction, but you also have now this repulsive interaction, right, between the two chlorines and the two hydrogens. Doesn't this all cancel out? And the answer is no, and that's because of this. That is, that the positive end of one molecule and the negative end of the other, so this distance and in this distance on the opposite end, they're actually closer together than the positive charges. So the yellow distance here is smaller than the distance between the two hydrogens, is smaller than the distance between the two chlorines. And so it's this attractive interaction that wins out, actually. So when you put those two dipoles together, you know, the repulsion actually, it's there, but it's the attractive interaction that wins out, and the whole system is stabilized because the distance between the unlike charges is smaller than the distance between the like charges. Okay? Okay, now, it also turns out that we have a functional form for the dipole-dipole attractive interaction. And that attractive interaction turns out to be a minus 1 over r cubed dependence. And this is exact. You can actually derive this. You can show that this is the interaction between two permanent dipoles is 1 over r cubed. The quantity on the top here, mu, hey, that's not a reduced mass this time. If we go back to when we started talking about dipole moments, this is the dipole moment of the molecule. hey, we got to use our symbols for multiple quantities. So that's the dipole moment. We're talking about dipole-dipole attractive interactions. And that attractive interaction looks like this, right? Minus 1 over r cubed. Now, you might say, where's the repulsive part of this interaction? In the case of the Leonard-Jones potential, remember we had two parts. We had the attractive part and we had the repulsive part. The repulsive part was 1 over r to the 12. The attractive part was 1 over r to the 6th. But it turns out that for dipole-dipole interaction, we don't have a general form for the repulsive part, unlike induced dipole. So the best we can do in general is to tell you that the dipole-dipole attractive interaction is 1 over r cubed. Okay? But I want to compare this 1 over r cubed to the attractive interaction due to the induced dipole interaction. You see that the dipole-dipole interaction is what we call longer range than the induced dipole. What I mean by that is that the value of r here, the distance between the two dipoles, can be larger in the case of a longer range interaction. It can be larger and still have some non-zero quantity for the interaction potential. So for example, if you're out here, at this value of r, you can see with a shorter range interaction, a 1 over r to the 6th, that the attractive interaction is only the difference between the pink curve and the black curve, which is 0. Whereas with the longer range interaction, hey, we've got more attractive interaction. This is more negative. That energy difference is larger. That's what we mean by a longer range interaction. All right, and I want to just compare in this diagram here the strength of the dispersion interaction to that of the permanent dipole-dipole interaction by comparing the interaction between two argon atoms to those between two HCl molecules. Argon only has the dispersive interaction between it because it doesn't have a dipole moment. And you can see that this well depth here is 1 kilojoule per mole, roughly speaking. But in the case of HCl, hey, that well depth here is 3 kilojoules per mole because that has a permanent dipole. And in both cases, HCl and argon-argon, we're talking about roughly the same number of electrons, not exactly, but roughly, right? Meaning the polarizability is roughly the same, right? So the dispersion interaction energy is roughly the same for HCl as it is for argon, but the difference here is that HCl has that permanent dipole moment. Therefore, the deeper well depth, therefore in HCl, the higher boiling point, 239 degrees Kelvin as opposed to 87 Kelvin for argon. Okay, and what's on this slide is just an example here of how that dipole-dipole interaction energy varies with the dipole moment. The larger the dipole, of course, the larger the interaction energy. So here I show you several molecules which have all, again, roughly the same number of atoms. They have the same mass, so they roughly have the same number of electrons, so they roughly have the same polarizability. The induced dipole is the same. But what's changing here as I go down is the dipole moment. So for propane, dipole moment really small, 0.1, divide. Dimethyl ether, 1.3. Acetaldehyde, 2.7. Acetonitrile, 3.9. Dipole moment increases, the boiling point increases, all right, because that attractive interaction is increasing. It scales roughly as the dipole moment squared, okay? Okay, so the dipole-dipole interaction is stronger. Now, I just want to briefly then remind you about one other attractive interaction that we have talked about before, and that is between two ions. Right there, we're talking about the Coulomb interaction energy, where the dependence is -1/r. Hey, that's the longest range interaction. And again, you can see this way out here, right? If I choose this value of r, the 1/6 interaction term would give me a very small value for the attractive interaction, because it's 1/r⁶. You take a large number for r and raise it to the 6th power and put it in the denominator. You're going to have a small value for u of r. The 1/r⁴ gives you some interaction energy, but 1/r, hey, that gives you a lot of attractive interaction there, right? It's the longest range. And you can also see here in a moment that it's going to be the strongest interaction. So here, what I'm just doing is comparing several molecules or atoms. Here's argon 2, which has only the dispersive interaction. Here's the plot, well depth -1 kilojoule. Then there's the HCl interaction energy that has the dispersion interaction in it, but also the dipole-dipole permanent interaction. It's -3 kilojoules. And then here we're talking about chlorine 2. Hey, this is a covalent bond, right? That well depth down here, this is no longer a Leonard-Jones potential energy, but this well depth here is, -200 kilojoules per mole. And then finally, this ionic interaction between potassium and chlorine. Hey, look at how strong that is, -450 kilojoules per mole. All right, so this is the relative strengths here of these interaction energies. Okay, so that's all that I want to say about these kinds of intermolecular interactions where we're dealing with some kind of dipole. But before we move on, I want to talk about one other kind of intermolecular interaction potential. And actually, you have to find it. And that's something called hydrogen bonding. Okay. All right, so a final intermolecular interaction, hydrogen bonding. Okay, hydrogen bonding here occurs between a hydrogen atom that is attached to an electronegative atom and another molecule in the gas or in the solution. All right? So the first requirement is that you have hydrogen attached to a very electronegative atom. So hydrogen bonding occurs for hydrogens attached to oxygen, nitrogen, fluorine. Those are all electronegative atoms. So water is a good example. All right? So in the case of water here, you have hydrogen bonded to this oxygen. And this oxygen is really very electronegative. All right? So what that oxygen does is that it pulls the electrons away from the hydrogen. So this hydrogen is kind of partially unshielded. It's partially deshielded. All right? And then there's a lot of electron density here on this oxygen. Well, because that hydrogen is partially deshielded, and because it's really small, this hydrogen actually will kind of see the oxygen on the oxygen atoms on a neighboring water molecule. And since this is kind of partially negative, right, this hydrogen will interact with one of the lone pairs on this oxygen, and it will form a bond. All right, this is a little bit partially positive, this is a little bit partially negative, and the result here is a bond between the hydrogen and the oxygen. And that bond is on the order of 20 to 60 kilojoules per mole. Hey, this bond is not a covalent bond. A covalent bond is 400 kilojoules per mole. This is 10% of it. But it's still a very important quantity, or a very important phenomenon, this hydrogen bonding. I mean, the hydrogen bonding is certainly responsible for the peculiar properties of water, as you'll learn more about in 560. But it's also responsible for the unique shape, oftentimes, of biological molecules. The helix in DNA owes its structure to hydrogen bonding. The hydrogen bonding is what makes trees stand upright. You know, the cellulose, the long cellulose molecules in trees are actually bonded together by hydrogen bonding. Nylon owes its strength to hydrogen bonding. And hydrogen bonding is also responsible for whether or not you have a bad hair day. So as an example of that, I want you to look at the slide up there on the walls. And what you see is a protein molecule. This is the structure of hair. The molecules that make up the strands of your hair look like this. It's a polymer. Well, it's a polypeptide. This unit right in here, carbon-oxygen, bound to carbon-hydrogen, bound to nitrogen-hydrogen. That's the peptide. It's repeated. You see the next unit over, COCHNH. COCHNH. Hey, that keeps repeating. That's the repeat unit. All right? And of course, this carbon-hydrogen right there, well, you can see it's got a line there indicating that it's bonded to something, and it is bonded to something. If that carbon-hydrogen is bound to another hydrogen, well, then you have a polypeptide, which has been made from an amino acid that you know of, or you might know of as glycine. If that carbon is bound to a CH3 group, then that peptide was made from an amino acid that you might know of as alanine. And if it's bound to a CH2SH group, well, that was an amino acid from known as cysteine. But what I want you to notice here is that these hydrogens on the nitrogen, hey, that nitrogen's an electronegative atom. And that hydrogen here, if your hair is wet, it's actually hydrogen bonded to a water molecule. Here's that hydrogen bond, right? And then in the next strand over, well, this oxygen is hydrogen bonded to a water molecule when your hair is wet. And the bottom line is that when your hair is wet, you've got the strands of your hair which kind of slip by each other. There's no registry of one strand to another because each strand has this coating here of water molecules due to hydrogen bonding. Okay? But suppose you take your hair and then you put it in a very contorted configuration like this. Okay? And then you drive off the water molecules. You dry your hair, right? What happens is that these water molecules then leave. The hydrogen bonds are broken. This is not such a strong bond, right? 20 to 60 kilojoules per mole. Those hydrogen bonds are broken. And then this hydrogen on this nitrogen looks around and it sees the oxygen with its lone pairs, right, on this strand. And so you form a hydrogen bond between this strand and this strand. And so now the strands of your hair are in registry with each other. They're actually stronger. And you know, they do tell you not to brush your hair when it's wet because it isn't so strong. Well, it's not so strong because these water molecules are insulating each one of these strands. And when it's dry, hey, these water molecules now are bound to each other. Or these two strands are bound to each other. They're in registry with each other. And so if you do this right, and you then let go of the contorted configuration, which I'm having trouble doing, okay, hey, those strands are in registry with each other now, and you have a good hair day. Okay, so that's the importance of hydrogen bonding. I didn't curl my hair just for this demo. A little asymmetric here. Okay, but now, if you are as fortunate or unfortunate, depending on your preference, to have curly hair, naturally curly hair, well then what you've got are a lot of sulfur-sulfur bonds, right? Right. You've got a lot of cysteine peptide groups. So what happens there is this. On these CH groups, right, you've got CH2 sulfur H. And on the next strand over, you have SCH2 and CH bonded to nitrogen, bonded to a CO, right? And you actually have a covalent bond between these two sulfurs here. This is a strong bond. The strands of your polymers in your hair are in registry all of the time. And if you want to make your naturally curly hair straight, you have to do drastic things like use drastic chemicals to break this sulfur-sulfur bond. Right? You can do it, but boy, it's not easy. And likewise, if you have naturally straight hair and you want to curl it, make it semi-permanently curly, well, then you've got to build in these sulfur-sulfur bonds, and you have to do, again, some rather drastic chemistry to make that happen. All right? Hydrogen bonding's important, especially if you go to do anything in biologically related sciences. You'll see that. Okay. So now I'm going to change topics here. And, yeah, I actually got to write on the board first, sorry. I'm going to change topics, and we're going to talk a little bit about thermodynamics in preparation to get up to chemical equilibrium so that Professor Cummins can come in on next Wednesday and start talking about acid-base equilibrium. So he's great. You'll love him. Okay. We're going to review some thermodynamics today. I'm going to go kind of quickly, okay, because some of this I think you know, but I want to make sure everybody's on the same page. First of all, bond energies. We talked about bond energies here as delta E sub D, and we measured it from the bottom of the well. And I told you a few days ago, I lied to you, the measured energies are really from V equals 0, okay, and they are. But what I'm going to do is I'm going to change my language. I'm going to, instead of talking about energies, I'm going to talk about enthalpies. I'm going to talk about delta H's rather than delta E's. And the reason I'm going to do this is because it's easier for us to measure a bond enthalpy than a bond energy. And that has to do with the fact that we usually make measurements in bulk under constant pressure conditions. And that's the quantity that comes out. Now, the relationship between delta H and delta E is this. Delta H is equal to delta E plus delta PV. This is a relationship that you will learn about in a lot of detail in 560 in chemical thermodynamics. At this point, we're going to take it as a given. For gases, delta H differs on the order of 1 to 2% from delta E. It's not much, but if you're doing some precise calculation, you need to be aware of that. Okay? For liquids and solids, delta H and delta E are really the same for all intrinsic purposes. Delta PV term is really very small. And in thermodynamics, since we're always, well, most always, looking at changes in energy, we need what we call standard states. And we're going to put a naught here on all of our delta H's to designate the standard state. And our standard state that your book uses and will use refers really to the pressure. And the pressure is 1 bar. Okay? And 1 bar is equal to 10 to the 5 pascals. That's equal to 10 to the 5 kilograms per meter second squared. Okay? The delta H's we're going to talk about are also just about all of them measured at 298.15 degrees Kelvin. All right, delta H does depend on temperature, but we're actually not going to look at that in the next few days. You're going to do that in 560. So our delta H's are going to be delta H's at 298.15 degrees Kelvin. Okay. All right, so on the first slide here, I show you a bunch of bond enthalpies for CH bonds. And of course, those bond enthalpies are a little bit different depending on what molecule you have, but they're not that different. And so what's often done, and your book does this, is that somebody goes and they calculate the average of the bond energies for lots of CH bonds and lots of molecules, and they prepare a table that looks like this. This is the mean bond enthalpy. And they have CH, CC, carbon, carbon, right? But these are average bond enthalpies. All right, but now, why are bond enthalpies important to us? Well, they're important because they determine the enthalpy of a chemical reaction, right? If the bonds are stronger in the products than in the reactants, that is going to give us an exothermic reaction. If the bonds are stronger in the reactants than the products, that gives us an endothermic reaction. And so let's look at this reaction. Hey, this is an important reaction. This is the oxidation of glucose. This is a reaction very exothermic, minus 2,816 kilojoules per mole. It is a reaction that is being carried out in your body, in every cell of your body as we speak. It is the reaction that's providing the energy to maintain your body temperature, the energy to move your muscles, the energy to repair tissue, the energy to think. All right? Important reaction. This is the reason why we eat. This is the reason why we breathe. This is the reason why we exhale, and this is the reason why we pee. Okay, so what do we need to do here to calculate the enthalpy for this reaction? Well, we have to figure out how much energy is required to break all of the bonds of the reactants, because that's how much energy we put in. And we have to figure out then how much energy we get back when we form the product bonds. Bottom line is the enthalpy necessary to break all the bonds you can calculate as 12,452 kilojoules per mole. That number comes from using these average bond energies I told you about. We can then get back some energy, minus 15,000 approximately, when we form some new bonds. That number comes from those average bond enthalpies. The difference between these two energy levels is the exothermicity of the reaction. Okay, now what did we do to get the enthalpy? Well, what I did is I took the bond enthalpies of each bond of the reactants, summed them. Then I took the bond enthalpies for each one of the products, summed them, subtracted the two to get the enthalpy of the reaction. I want you to notice something here. Important. This is reactants minus products. In a moment, I'm going to show you another way to calculate the enthalpy for a reaction, and it's going to be products minus reactants. You got to know this. Okay. But you also see that the calculated enthalpy was not the experimental enthalpy. Why? Well, because we used the average bond enthalpies. We didn't use the exact bond enthalpies because, hey, you know, if we had to use the exact bond enthalpies, can you imagine the size of the table of data we would have to have? We'd have to have a bond enthalpy for every bond for every known molecule. That's a lot. So what are we going to do? Is there a more accurate way to do that? Well, yes, with knowing the absolute bond enthalpies. But that's too much data. So is there some other way to do it? Yep. We're going to use heats of formation. Okay? All right. A heat of formation, delta H naught with an F as a subscript. The heat of formation is the enthalpy of a reaction that forms 1 mole of a compound from the pure elements in their most stable form in their standard state. So for example, here's water. We're forming 1 mole of water from its elements, hydrogen and oxygen. The enthalpy for this reaction here, the enthalpy for that reaction is defined as the heat of formation of water. Why is this the heat of formation of water? Well, because we're forming 1 mole, and that is important, from the elements that make up water. What elements are they? They're hydrogen. But notice that this hydrogen is H2. It's not hydrogen atoms because H2 is the most stable form of hydrogen. Oxygen. It's O2, not oxygen atoms, because this is the most stable form of oxygen at 1 bar pressure. Right? Look at this here. What's the heat of formation of oxygen? Well, the enthalpy change for this reaction is 0. That's the heat of formation of oxygen. Why? Because we're forming 1 mole of oxygen from the elements in their most stable form. Right? So for elements like oxygen, hydrogen, nitrogen, chlorine 2 in the gas phase, hey, those all have heats of formation that are equal to 0. And then finally, here's the expression that, or the reaction that gives us 1 mole of glucose. The enthalpy for this reaction is the heat of formation of glucose. We get it from its elements, hydrogen, oxygen, and look at the elemental form. The most stable form of the element carbon is graphite. Okay? Is there an 18-0-something exam? Yes? Okay. See you on Monday.